Hello everyone, my name is Ho-Jung Lim. I serve as Director in R&D Design Center at Amco Technologies. Today I'm gonna discuss the design of a system module package for power distribution network. A system module package is very similar to board level circuit. It integrates a system function in the package beyond a system package we call SIP. It is an advanced IC packaging solution to enhance the PDN and achieve small form factor. Let me present the item in this agenda today. First, I'm gonna introduce the subsystem module. Secondly, compare a double-side component placement motherboard with the subsystem module. And I will address the pros and cons. Third, review DC IR drops result between regular motherboard and subsystem module and how and what the big differences are. Also, I want to address the optimum decap combination for lower impedance profile in frequency domain. This is a very important in system PDN design in terms of package size, cost reduction. Lastly, I will summarize all mentioned above to conclude this topic. Why do we need a subsystem module? Today's mobile device platform is constantly evolving due to 5G, AR, VR, and use of a personal mobile device in workplace and everywhere. Also, mobile device is changing with new design elements like a user experience and even new phone shapes. As a result, future mobile device will come in many different form factors. All those new mobile device platforms are powerful. They are not only confront serious power integrity challenges, but also electrical power delivery of system. This is increasingly considered in systems high-speed performance. Devices become more sensitive to noise of power and ground plane. The mobile device in industry has used motherboard with single-sided component placement PCB or double-sided component placement PCB. It provides power distribution network challenges such as controlling, mounting, or spreading inductance because of a number of layer count and larger size of motherboard. So in order to mitigate these issues, novel device packaging such as a system module package is necessary. Subsystem module can integrate a single function with multi-chips and component into single package, and it can provide a shorter power decoupling path and small form factors. We can take advantage of major three topics today. First, small form factor. Second, power distribution network improvement. Third, of course, low cost. For low cost with PDN performance, unlike a motherboard design with a decoupling capacitor, the subsystem module package system needs to redefine the role of the capacitor and its configuration for PDN performance. Specifically, the design of package form factors should include careful consideration of optimal PDN performance and the number of components which need defined decoupling capacitor value and the placement strategy for low impedance profile with cost some benefit. Subsystem module wouldn't always be the best, but it is better when we design effectively in terms of integration of power plane, component placement, and capacitor configuration. Now I will discuss both static case and DC IR drop and AC analysis in precursor domain with these three topics. First, I will highlight the role of simulation in the subsystem module design for this PDN. Secondly, I will compare the performance of a double-side component placement we call DSCP motherboard with the subsystem module package. And then prove the advantage of subsystem module package. Finally, I will introduce three terminal decay configuration of capacitor size, count, and value for the subsystem module package in order to decide the optimum performance and package density based on cost-effective model. This cross-section shows a DSCP PCB with quad motherboards. It has more than 12 layers with a thickness greater than 650 micron. As you can see, the component has been placed on both top and bottom. AP pop is mounted on top and PMIC placed directly underneath the AP on bottom in order to reduce mounting space and spreading inductance. This is a cross-section that shows a subsystem module. It is much smaller than motherboard design DSCP, and it uses ultra-thin quartz 8-layer substrate with a thickness less than 400 micron. Cap and inductor were mostly placed on top layer since BGA boards were populated on bottom layer. And the AP and memory were placed on bottom. PMICs were placed on top above the AP. It enabled very short coupling paths between PMIC and APs. This design scheme can reduce spreading and mounted inductance. This is what a system module looks like. As you can see these pictures, system module can manage a tight gap between the component and die and thin dielectric for shorter electrical paths. The gap between 05 035 is only 105 micron. This is much tighter than PCB level component placement. The gap between 05 035 and die is 150 micrometers. The power ground connection to a package device are often located near the package center. So we estimate the spreading inductance per current from a distribution of capacitors to get to this central location. So if there is a tight rule between die and caps, we can reduce spreading inductance based on these formulas. The DSCP model contains the impedance on motherboard starting from voltage regulator to IC package. It includes the solder balls to die bumps and the return path from die bump to PMIC ground pins. In the DSCP model, impedance of series RLC can be determined by this formula, and this IR drop of each rail can be obtained using this formula. The subsystem module contains all DSCP aspects to integrate the system function of AP and PMIC in a package. Since the total impedance is consolidated to a single package, it has low impedance and simple equation. The total impedance GPDN MD is regarded as GPDN package, and it is connected from voltage regulator to die bumps, and its return path is from die bump to PMIC ground pin. In the subsystem module model, the impedance of series RLC circuit and DC IR drop of each power level can be determined by this equation. DCIR analysis of voltage drop leads to improved system quality. This table shows the comparison of DCIR drop between subsystem module and DSCP model. Total transmission line length in subsystem module is connected from the bump head of voltage regulator on the PMIC to bump head of AP chip. It can be significantly reduced. Although power rails IR drops in subsystem module is higher than DSCP model, the ground rails IR drop in subsystem modules can lead to lower value than DSCP model. Because the subsystem module design can be large and have a number of ground planes and small form factor. This can provide a return path that is much better than the DSCP model. Consequently, each rail of IR drop in subsystem module was improved by 30% up to 20% compared to the DSCP model with the package. The ratio is improvement is not that important because it depends on layout design strategy and expertise of designer. The important conclusion is that the subsystem module can provide a reduced total IR drop. Also, the peak impedance formula is telling us that there are direct correlations among ESR, ESL, and spreading inductance. The spreading inductance and cavity is related to the package design layout. ESL is all about the cost. But ESL is not much related to what I have mentioned above. So if the capacitor ESR maintain higher, Q factor of cavity resonance reduced, and peak impedance lower when we cannot control spreading inductance or ESL. The goal in power rail impedance is to push the peak frequency above bandwidth and to reduce the impedance peak below target level. While the subsystem module achieves the lowest spreading inductance and mounted inductance and provide a short path between capacitor and chips. The number of capacitor and their capacitance must be considered. Instead, lowering the ESR to reduce peak impedance is a more effective way if subsystem module had low mounted and spreading inductance, because all capacitors are placed directly underneath chip or as close as possible to PMIC. These two graphs show the difference of peak impedance in package, with the ESR changed from 1 micron ohm to 10 million. Because of cost and package space limit, these are practical concerns in real product design, and a limited number of capacitors are added to package. The most effective way reducing peak impedance is package is to use controlled ESR capacitor instead of increasing capacitor value or multiple capacitor in parallel. This slide explains another way to reduce peak impedance by Decap configuration variant in subsystem module. The fact is the highest capacitor value is not always going to give us the lowest impedance system. Also, optimum combination of decap in motherboard is not the best for the subsystem module since all environment has been changed from motherboards. This plot shows impedance profile with bulk capacitor for all variants. Leg number 2 to number 8 show similar impedance and peak impedance trend compared to the leg number 1 that is added only 2 microfarad or 201 capacitor. Leg number 2 to number 8 have less impact on the impedance peak compared to the number of capacitor and value from 3.3 microfarad O4O2 and 15 microfarad O5 O35. The O4 O2 and O5 O35 are 3-terminal capacitor for low ESR, but the O2 O1 is just regular 2-terminal capacitor. The main advantage of 3-terminal capacitor over the traditional 2-terminal capacitor is only reduced ESR. It leads to lower PDN impedance and improved PI. In this result, this table shows a cost saving by reducing capacitor count. This plot shows the impedance profile with VRM and bulk capacitor for all variants. Although the O5-O35 15 microfarad capacitor is the largest capacitance, leg number 4 to number 8 show a lower second impedance peak at high frequencies than O5-O35 on leg number 2 and number 3. This shows that using a larger capacitance to suppress the impedance peak is not an effective way. And larger is not always better, especially if mounted and spreading inductance are extremely low. The subsystem module can achieve low mounted and spreading inductance due to a tight gap between component and die and thin dielectric. Another factor to reduce impedance peak is to take advantage of a MLCC with higher ESR in order to damp some of the parallel resonance and manage the impedance peak. Unlike motherboard, mounting inductance in this case is relatively low, so ESR could provide an optimum capacitor value. Leg number 6 to number 8 use on-chip decoupling capacitors. This enables a design for lower target impedance, but it comes at a higher cost. But the subsystem module with on-chip decoupling capacitor did not deliver that much lower peak impedance because it already has lowest mounted inductance. This plot shows how more on-chip decoupling capacitors are not always the best. We found that leg number 4 is the optimum set of capacitor based on package density and cost factor as shown in this table. Leg number 5 could be second set of capacitors. Difference between leg number 4 and number 5 in this plot is around 1 ohm, and leg number 4 push the peak impedance up to 2.28 to 2.88 GHz. The percentage of density represents the size of package that provide opportunity for relaxed design rule and reduce the package form factor. The cost can be reduced based on the number of components and component cost. As a result, leg number 4 and number 5 meet the 3 different objectives for impedance, form factor, and cost. The subsystem module is a package assembly level design which has more microvias, a thinner dielectric, and tight component placement capability for the chips. As a result, the subsystem module can achieve low mounting inductance, which is related to the surface trace length, capacitor body size, and via path for the power and ground. It also can enable was designed to have a lower spreading inductance than DSCP model. The subsystem module improved the DC-IR drop result because it enabled a shorter electrical path from PMIC to AP chips than DSCP model. The impedance profile with Decap variant at frequency domain was reviewed. It showed a combination of Decap managed to lower peak impedance. The most effective way is to maintain ESR as low as possible when the module package's ESR optimization reaches to the saturation point. Using a number of decaps or large value of decap did not have a significant impact on PDN. Consequently, we suggest an optimum combination of decaps for cost savings and small form factor design. Once decap configuration is optimized, on-chip decoupling capacitor will only have a small impact on PDN. Even a DSCP model experiences power integrity challenges due to many PCB layers, component placement difficulties, and long decoupling passes. This topic has reviewed the advantage of a system module that can improve power integrity performance with the optimum design and capacitor combination. Optimized capacitor configuration met not only target peak impedance, but it also reduced cost and form factor size. These analytical results can be used in design guidelines, which can be estimated in pre-manufacturing process of subsystem module packages. This is the end of slide. If you have any questions or would you like to learn more about this topic, please feel free to contact or email me below address. Thank you.